That would be why I did it for today. Uh, can email it to you right now.
Okay.
I looked at it. I could swear I looked at it and made sure. Well, how was the birthday party?
Oh, it was great. Yeah, it was. Yeah, it was. It's great because like as a new parent, you don't really get to see your friends all that much, and so the first birth. I mean, the kid is never going to remember his first birthday
No.
party, but it's more about bringing your friends and family together. So
Yeah.
if only it wasn't so hot. That was the only thing. People were like getting heat stroke out there.
Yeah, the first birthday party is all about the parents.
Exactly.
Yeah, I full one did.
Happens to the best of us. Got it.
Great.
All right, it's 3 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Everyone's going good. Okay, so we are in week 4 out of 5, and so we are very quickly approaching the crunch time for the summer session. So some announcements. So I think one thing probably you've all noticed, but I've finished grading your midterm projects. So those grades should be up on Canvas. I also uploaded the rubric for each of you as well, so you can kind of see how your grade was broken down. If you open up the rubric, I also tried to leave as much comments and feedback as I could. So please take a look at those. That feedback will be very relevant for the final project, because final project will be very similar to the midterm project with just a few additional requirements. So we'll talk about the final project probably on Thursday of this week, just because that's also coming up very quickly. But first thing I want to talk about today is the midterm exam. All right. So midterm exam is planned for 1 week from today. So it's going to be on Tuesday, July 28th. So that is an in-class exam. Now, normally this exam is I design it to be basically just taken one day in a regular semester class. And so it's a 75-minute exam. But I mean, you guys get the benefit of this class being a 3-hour long class and us kind of being a little bit ahead of schedule. So I'm going to give you guys the entire 3-hour class session to do the exam. I'm not going to make the exam longer because that makes more grading for myself. The format for the exam is going to be basically 4 short answer conceptual questions and 3 direct stiffness problems. That's kind of the standard format for this exam. In terms of the content that's on the exam, I did post a study guide today. So that is available on Canvas. And so if you check the weekly page for week 4, part 1, you'll see it's the very last document on the page for the study guide. So please take a look at that. The study guide is not that long. It's the midterm exam will really just only cover just the direct stiffness stuff. So nothing about ANSYS or anything like that. It's really just on the conceptual stuff that we've been going over for the last few class sessions. So the study guide is not that long, but the exam can be a little bit lengthy just because these direct stiffness problems do take a while. And so, even though you guys will be having longer than a typical semester class, but you definitely want to be efficient with your time as well. Okay. In terms of what you can bring for the exam next week, you can bring a writing utensil, of course. Please bring a calculator. I don't have a spare calculator, and so please make sure it's in your bag before you come to campus. And so I don't have another one to give you. Not that not having a calculator will make the exam impossible. But it is good to have just to kind of speed up some of the calculations. And you can have one 8.5 by 11 sheet of notes. And I forgot to write on here. You can write on both sides. Okay. You can write it, you can type it, you can put whatever you want on the note sheet. The only thing you can't put on there is the answers to the exam, which is impossible because I'm probably not going to write it until the last minute. And so you can feel free to put anything you want on that note sheet. Okay. Now, your main practice for the exam is going to be the problem set. And so I did just post that yesterday. So the problem set will be your chance to practice these direct stiffness problems beyond kind of the examples that we do in class. And so that was posted yesterday. That is due this Sunday night by 11:59. So I will post solutions for it. I know it's a little bit of a short turnaround just because homework is due on Sunday and then exam already is on Tuesday. But I will try to stay up late on Sunday just to post the solutions for the homework, just so that you can have that available to study on Monday and for Tuesday before the exam as well. Okay. Okay, so please plan on being here next Tuesday, July 28th. That is the only day of this semester that I require you to be in class, just because there's no mechanism for me to give the exam virtually. Okay. Okay, questions. Question in the chat. So will there be any ANSYS conceptual questions, or will the problems be most in what we've been working on? Yeah, so there will be nothing on ANSYS. And so the starting point for the exam is going to be all the direct stiffness stuff. Yeah, so it's really just on the theory and concept behind finite elements, nothing on the application. Yeah. All right, any other questions on the exam or just anything that we've been covering so far? Okay. All right, so yeah, so next 2 weeks going to be pretty busy in this class. And so, we have midterm exam next Tuesday, and then final project is going to be due not this Sunday, the Sunday after that. And so please make sure you guys are on top of everything. Next couple weeks are going to be busy. We'll talk about final project probably on Thursday, just because, I want to make sure I finish the direct stiffness stuff first. But just to kind of give you a little bit of a preview, the final project will be very similar in structure to the midterm project, where you'll be conducting basically what I would consider, a full, front to back, finite element study. The only difference is that for the final project, you will have to come up with your own geometry. And so, you can either use a geometry based on maybe a project that you're working on already. And so I know a lot of you who are in senior design, you can use a geometry that you are thinking about for your senior design, or maybe something that's inspired by it. You can use a CAD file that you've maybe had from another class before. Or maybe a CAD file that you find online. So, the main difference is that, you'll be coming up with your own geometry, which then gives you more freedom in terms of how you define your project objectives, okay? There will also be a few additional requirements as well for the final project. One of which is that you'll be required to do a mesh convergence test for the final project. So, that's something that we've discussed a bit in class so far. And you'll also be required to do what's called a validation calculation, which we will do next week. Okay, but besides that, it's very similar to the midterm project, but we'll cover in more detail on Thursday. Okay, but I just want to kind of mention it today, just so that you're kind of start to maybe think about kind of what kind of geometry, what kind of subject that you want to do for your final project. Okay. Okay, all right. So with that, let's go ahead and pick up where we left off from last Thursday. And so last Thursday, we kind of left off in kind of in a little bit of an awkward spot because we were kind of right in the middle of an example. So let's kind of jump back there and kind of continue onwards. Okay. Okay, so the last kind of major thing we talked about last Thursday was, discussing how to do 2D direct stiffness problems involving trusses and springs. Okay. So we basically took our one-dimensional kind of theory in direct stiffness and just extended it to 2 dimensions, right? The main difference now is that we now have to compute deformations both in the x and y directions, all right? And so that's something that's a big part of our calculations, and that also changes the structure of our element stiffness matrix as well, right? Where now our element stiffness matrix has to account for the orientation of the element as well, okay? So the example that we're working on was this one here. So it's a 3-element system. We have 2 truss bars, elements A, element C, and a spring, element B, right? And they're oriented based on the figure that is here. Okay. All right. And so where we left off last time was the computation of the element stiffness matrices. Okay. So even though doing 2D problems does require more work in the fact that there's just larger matrices to compute and more things to plug in, the overall process that we follow in order to do a direct stiffness problem is still the same, right? So we're going to start with the element stiffness matrices, then we're going to move on to assembly of the elements into one global linear system, apply the boundary conditions, and then solve from there. Okay. All right. So let's go ahead and pick up where we left off. Okay. And in fact, we kind of left off at a good spot because we had just finished computing the element stiffness matrices for elements A and B. And so let's just kind of refresh our memory and compute the element stiffness matrix for elements C. Okay. Okay. So for the element stiffness matrix for a 2D truss, remember it is a 4x4 matrix, right? And it's given by the following expression. And so we have basically, we're going to be computing lots of sines and cosines of the angle on which the element is oriented from. Okay. And so, I have it written up here. In fact, let me just kind of wrote this down here if I can. Let's go ahead and write this downwards. Okay. All right, so that's our element stiffness matrix for a truss bar, right? So every C that you see there is cosine of the angle that the element makes. Every S is a sine, right? And so we have different combinations of sine and cosine. Okay. Now, of course, this isn't fully the element stiffness matrix here because remember we have to adjust the degrees of freedom here according to the nodes that it's connected to. Okay. And so for element C, we know element C is actually connected to nodes 1 and 4. Okay. Okay, so let's adjust that. And so based on that, we know that we have to adjust the node numbers for the second node here. So instead of D2X, D2Y, it's D4X and D4Y. Okay. Okay. And remember from last week, we found that element C has an orientation angle of 0 degrees because it's a horizontal element, right? And so we come back up here, right? Element C is this one here. And so if we compute the orientation angle for this for a horizontal element, the angle is 0 degrees. Which is convenient for us because for 0 degrees, cosine of 0 degrees is 1, sine of 0 degrees is 0. And so that simplifies our calculations quite a bit, okay? Okay, so let's just go ahead and plug in for here, for this. Oh, we have AE over L. AE over L is the same, so that's 5 times 10 to the 5th, same as element A. Okay, so we have 5 times 10 to the 5th. Okay, so let's start plugging in sines and cosines here. So first we have cosine squared. Cosine of 0 degrees is 1, so 1 squared is 1. Okay. Next we have cosine times sine, 1 times 0, which is 0. Next we have minus cosine squared, which is a minus 1. And then a cosine, minus cosine times sine, which is 0, because that's minus 1 times 0. Okay. All right, so that's the first row in our matrix. And then before we move on to the next, remember what we always do is that we take advantage of the symmetry of the element stiffness matrix. And so as soon as we write things in the first row, we're going to write those exact same entries into the first column. Okay. So basically, we're going to take each entry here and just kind of rotate them downwards, just like that. They're going to fill in all the entries for the first column. Okay. So right under the 1 in the top left, we have a 0. Next, we have a minus 1. And then a 0. Okay, so that's the first row and the first column. Next, we have the second row. So second row, we have a sine squared. Sine is 0, and so 0 squared is just 0. Next, we have minus cosine sine, which is 0, and then minus sine squared, which is 0 as well. Okay. All right, and so we're going to do the exact same thing. And so we're going to write those entries into the second column. And so we're going to go just like that, just like that. Okay. Drop those down in there just like that. All right, next we have the third row. So third row is we lead with the cosine squared in the diagonal entry. So that is a 1. That's 1 squared is 1. And we have cosine squared, which is, cosine times sine, which is just 0. Write that into the third column. And so we have a 0 there. And then finally, we have a sine squared in the bottom right corner, which is just 0. Okay, good. So anytime you have an element that's oriented, that's either horizontal or vertical, it's pretty nice because a lot of the element stiffness matrix ends up being 0 because we take advantage of the fact that either sine of the angle is going to be 0 or cosine of that angle is going to be 0. Okay, so now we have our 3 element stiffness matrices, element A, B, and C. Right, so now we are ready for assembly. But before we start assembly, are there any questions on this example here? Okay, all right, so let's go ahead and get started with assembly. All right, and so just like we did with the 1D problems, we have to assemble all 3 of our element stiffness matrices into the same matrix, okay? Where this global linear system has all of the degrees of freedom from our elements. Okay? Now you have to be careful here because remember, the way that we used to do this in our 1D problems, we would just count the number of nodes, and then that gives us the size of our system. Okay, but remember for 2D problems, our nodes actually have 2 degrees of freedom, right? So for every node in our system, we have to compute an x deformation and a y deformation. So that means the size of our global linear system is the number of nodes in the system multiplied by 2, okay? Because our global linear system has to account for every degree of freedom that is available in our system. Okay? So in this case, for a 2D truss problem with 4 nodes, each node having 2 degrees of freedom, that means our global linear system will have 4 times 2, which is 8 degrees of freedom. So that's 8 rows and 8 columns. Okay, and so you want to make sure you give yourself enough room on the paper to write this, right? Now, granted, a lot of this global linear system is going to be 0, and so don't be intimidated by a large linear system. But we do have to at least have a space for them. Right? Okay, so let's make a very large matrix here. I'm going to give myself as much room as possible. Okay, and then first let's label the columns just to make sure we have everything. And so for every node, I'm going to go to label a column for the x deformation and the y deformation. Okay. All right, so we have d1x, d1y, d2x, d2y, d3x, d3y, d4x, d4. Okay, and then we have to write all of those degrees of freedoms into the rows too. Okay, so you have a d1x row, d1y, d2x, d2y, d3x, d3y, d4x, d4. Okay. And then one thing we haven't written here yet is the forcing vector. So that's f1x, f1y, f2x, f2y, so on and so forth. But we'll write that after. It's just kind of taking all the room here just to write the matrix. Right. Okay, so just like we did before, we are going to go through each of the elements and then write in the entries or insert the entries of its element stiffness matrix. Okay. So let's start with element A. Okay. So element A is connected to nodes 1 and 2. Right? That means all of the degrees of freedom associated with nodes 1 and 2. That means the x deformation and the y deformation is going to be part of this entry here. Okay. So let's go ahead and box that out. And luckily, node 1 and node 2 are right next to each other in the matrix here. And we can just make one kind of huge box just like that. Okay. We have to make a much larger box now because these element stiffness matrices are 4 by 4. Okay. Okay, so let's go ahead and write in the entries of this matrix here. And so if we look back in our notes, our element stiffness matrix for element A looks like the following. And so we have 0, 0, 0, 0, 0, 1, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0. Okay, good. All right, next we have element B. So element B is connected to nodes 1 and 3. Now this is not next to each other in the matrix, but we still need to insert it. And so we do have to break up its contributions. And so, we have to look and see, which areas are nodes 1 and node 3. Okay. All right. So first we have the entries which, we're going to the node 1 columns and the node 1 rows. Okay. So that's this portion right here. So we do have an overlapping portion with element A, which makes sense because both element B and element A are connected to node 1. And so it makes sense that there should be some overlap there. Okay, next we have the rows associated with node 1 and node 3. Okay, so that's D1X, D1Y, D3X, D3Y. So that section is right here. Okay. So that's the D1X, D1Y row, D3X, D3Y column. We have the same thing down here. Okay. And then finally the same thing right. Okay, so we do have to split it up, but hopefully it's kind of straightforward how we split this guy. Okay. Okay, so let's go ahead and add those entries in, right? And so if we go back up here to our element stiffness matrix for element B, right? The way we split it up is basically we took these 2x2 quadrants and kind of split them up into different regions of the global stiffness system. Okay. Okay, so for the upper left quadrant, that goes into the D1X, D1Y entries, and so that's all positive 1/2. Oh, I'm sorry. Before you start writing those in, I always forget this, right? Remember, we're not just writing in the entries in the middle there. We also have to account for the multiplier in front. Okay. Okay, so we can do this in a couple ways, right? And so if we want to keep the multiplier in front equal to 5 times 10 to the 5th, we can do that. Okay. And so basically we're going to say that there is a multiplier in front. Basically going to say in front here is 5 times 10 to the 5th. Right? So that way we don't have to rewrite the entries for element A, okay? But it is going to affect how we write the entries for element B, okay? Because element B, if you look at the entry in front, remember element B was associated with the spring, right? So the spring constant for the spring is different than the value for AE over L for the truss bars, okay? So instead of being 5 times 10 to the 5th, for the spring element B, it's 2.5 times 10 to the 5th, okay? Which is 1/2 of that. And so when we add those entries into the global stiffness matrix, then we have to account for that. And so instead of adding 1/2, we're going to add in 1.25, which is 1/8. Okay, so 1/2 divided by 2. Okay. Yeah. Okay. Okay, so let's go ahead and do that. Okay. All right, so we're going to add in a plus 1.25 plus 1.25. Oh, I'm sorry. Hang on. It's not plus 1.25, it's plus 0.25. I'm sorry, I have this a little bit differently than my notes. And so, because we are doing the 5 times 10 to the 5th out there, right? We have to have 1/2 of the 1/2, which is 1/4. I'm sorry. Okay, so let's go ahead and try that again. So we're going to add a plus 0.25 plus 0.25 plus 0.25 plus 0.2. Okay. Okay, that makes sense. Okay, and then over here, on the right here, we have everything that's negative. So we have the minus 1/2 out there. Okay, and so we have a minus 0.25, minus 0.25, minus 0.25, minus 0.25. Okay. Right, in the bottom left here, we have minus again. So you have minus 0.25, minus 0.25, minus 0.25, minus 0.25. And then over here, we have positive again. So this is positive 0.25, positive 0.25, positive 0.25, positive 0.25. Okay. Okay. So let me kind of explain that again, just because I was kind of all over the place there a little bit. Okay. Remember, when we add things to the global stiffness matrix, we want to make sure that all the values of everything that we're computing in is consistent. Okay. Now, the challenge that we had with element B was that the multiplier in front, okay, which is essentially the spring constant for that spring for element B, was half of the effective spring constant for the truss bars. Okay, so when we computed AE over L for the truss bars, right, which is essentially, well, have it here, right? So when we computed this AE over L for the truss bars, we got 5 times 10 to the 5th, right? Which was basically the value that we're putting in front of our global stiffness matrix, just like that, okay? But for the spring had a spring constant that was only 1/2 of that, which is 2.5 times 10 to the 5th, right? So 250,000 pounds per inch. And so the fact that these are, the fact that these are different here, one way that we can make them the same is we can factor out a 2. Okay? We basically factor out a 2 from the interior of the matrix and multiply that by the front. And so that gives us 5 times 10 to the 5th. But then that also changes everything in here, right? And so if we factor out 2, that means we have to divide everything within the matrix by 2. And so instead of 1/2, we have 1/4. Okay. Okay, so hopefully that makes it a bit more clear because I know I kind of messed that up a little bit. But so in the notes, what I did, so if you're curious what I did in the notes, what I had in front was just a regular, just 10 to the 5th, right? And so I basically just, eliminated that out. And then that kind of went from there. Okay. Okay, any questions on how we got this matrix so far? We have one more element to put in, but this is a good time to pause if you have any questions. Okay, all right, so then let's put in our last element, which is element C. Element C we know is connected to nodes 1 and 4. So that's going to be this region right here. Okay. So all 3 elements actually are connected to node 1, right? And so we kind of have a little bit of a busy party up at the D1x, D1y portions. Right? Okay, and that's going to be this portion right here. Right? That's D1x, D1y row, D4x, D4y column. Okay. It's going to be these last 2 rows here, and then these 2 rows in column Q. Okay, so let's go ahead and add in those entries. And just like before, we're going to take our element stiffness matrix, kind of block them off into 2x2 sections, and then scatter them to the different parts of the global stiffness matrix according to what they are. Okay. All right, so we start with the upper left portion here. We have a +1, and then a +0, +0, +0. Okay. All right, next we have the next portion, which is a -1, 0, 0, 0. And then the bottom left, we have a -1, 0, 0, 0. And then a +1, 0, 0, 0. Okay. And then just like before, everywhere that we haven't boxed yet, we're just going to fill in a 0 into those locations. Right? So you have a 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, just like that. Okay, and with that, our assembly is done. Well, technically, we could simplify this, right? And so, if we look at the upper left portion there, it's a little bit of a mess because we have a bunch of things added. Okay. So let's simplify this just to make it a little bit easier for us. Okay. Okay, and so if we add all of those together, and let me use green for this. Okay. And so if we add all those together, we have a 1.25, 0.25, 0.25, and a positive 1.25. Okay. So everything in green in the top left there, that was a result of just adding in the contributions from all three elements. Okay. Okay. Any questions on this so far? How we did the on how we did the assembly? Okay. All right. So next step here is we're going to do boundary conditions, and so let's just write them right in line here. Okay. Okay. And so for the boundary conditions, we do need a forcing vector here. So let me go ahead and write that in now. All right. So we have F1x, F1y, F2x, F2y, F3x, F3y, F4x, F4. Okay. Okay. All right. So let's start with the constraint type boundary conditions. Okay. So we have three constraints in this problem. Actually, this problem is actually very constrained. So if we go back up to the figure here, we can see that we have fixed constraints on nodes 2, 3, and 4. Okay. Right. So that means that all the deformations at those nodes are going to be 0. Okay. So that means d2x is equal to 0, d2y is equal to 0, d3x is equal to 0, d3y is equal to 0, d4x is equal to 0, d4y to 0. Okay. So that's quite a lot, right? And so basically every row that's associated with nodes 2, 3, and 4, we're essentially going to replace them. Okay. And since each of these nodes have 2 degrees of freedom, that means we're going to apply this boundary condition to 6 rows in our global matrix, which is a lot. Okay. Okay, so let's return to our global matrix. Okay. And so we're going to be affecting the rows of d2x, which is this one, d2y, d3x, d3y, d4x, d4. Okay. So all 6 of those rows we're essentially going to replace. So let me actually clear those out just so we can see this a bit better. Okay, so let's start with the d2x row. So for the d2x row, actually most of it's already in place, right? So we start by just replacing the entire row with zeros, which it kind of is already, right? And then we put a 1 on the diagonal. And so for d2x, which is the third row in our matrix, that means the 1 is going to go in the third column, right? The d2x column, right? Okay, and then on the right-hand side, we're going to turn f2x, we're going to set that equal to 0. All right, next we're going to apply that constraint to d2y, right? And so we're going to zero out the entire fourth row. That means this one and this one are going to be zeros, but we need to put a 1 on the diagonal entry, which is going to be the fourth column, which is just this one right here. Okay, and then just like we did previously, we're going to take f2y, set that equal to 0. All right, so we're just going to keep going like this. And so for rows 5, 6, 7, and 8, we're going to zero them out, put a 1 on the diagonal, put a 1 in on the forcing. Okay, so I'm just going to do that quickly, but feel free to kind of fill it in yourself quickly as well. oops, forgot F3y. F3y here going to be 0 as well. F4x, this row is almost there. One here, set F4x equal to 0. F4y mostly there. One there. And F4y going to be 0. Okay. Okay. So this isn't typical, or sometimes it is. So it depends on the problem. But for this particular problem, there's just a lot of constraints to apply. Okay, so just make sure that you apply them all just like that. Okay. Okay, so now let's get to the load. So for the load, let's kind of scroll back up here. So you can see the load, our load in this case is applied on node 1. Right? So the load is basically this guy right here. So we have a load of 10,000 pounds, but we have to be careful here a little bit because node 1, remember, we can deform in both the x and y direction. So not only do we have to identify the node where the load is taking place, but also the direction. Right? So in this case, the load of 10,000 pounds is being applied only in the y direction. Okay? So that means we're only going to have an F1y. So F1x is actually going to be 0. I have to write that in as well. And then F1y is going to be a minus 10,000. Okay. All right, so let's go ahead and write that in here. Okay, so for F1y here, let's go ahead and write in minus 10,000 for that. Okay. And then F1x is going to be 0. Right, and so with that, we are done, right? And so as soon as you finish applying the boundary conditions, that's as far as you can take it with the hand calculations, okay? And so from here, we can solve this system. But obviously with an 8x8 system like this is not something that you want to solve by hand. Although I guess technically this one's not so bad just because 6 out of 8 are going to be zeros. But I would still kind of prefer to solve this with the MATLAB. Okay. Let's go ahead and plug. And so if you plug this matrix into MATLAB, and so if we do that, what we get is d1x is equal to 0.0033 inches. Okay. d1y is equal to minus 0.0167 inches. So you can see here that most of the deformation is in the y direction, but because of how the truss structure is designed, there is actually some deformation in the x, even though our load is purely in the y direction, which is I think very, very interesting. Okay. All the other deformations, d2x, d2y, all the way through to d4y, are all zeros, okay, because of the constraints. Okay, so the only the only answer here that's kind of remotely interesting is that for node 1, because that's the only one that's not constrained. Okay, good. All right, so like I said, these problems not they're boring. I will say that, and they do take a while. Okay, so you can expect a problem probably maybe a little bit more difficult than this on the exam. So like I said before, you'll have the full 3 hours to take the exam, but you definitely don't want to dilly out. You want to kind of make sure you're working through the problems efficiently. Okay. All right, any questions on this example here? Okay. Okay, good. So I do have one more example of trusses, and so I do want to work through that, and we'll get through that before the break. But there is one additional kind of calculation that you can run from this analysis here. Okay. So just like in ANSYS, right? So usually when you run an ANSYS simulation, you're not just interested in the deformation, although the deformation itself is usually interesting. That's something you want to find out. But a lot of times if you're running a structural simulation, you want to know the stress, right? That's kind of why you run finite elements, or one of the reasons why you run finite elements is to get that stress. Right? So even with this kind of very simplified methodology here with the direct stiffness, there's a way for us to actually compute stress. Okay, so let's go over how to do that briefly. Okay. Okay. So how we compute stress in a truss bar, we kind of leverage the fact that we know truss bars can only support tension and compression. So since truss bars can only support tension and compression, that means the mechanical stress that the truss bar experiences is going to be purely normal stress. And so there's going to be no shear whatsoever. Okay. And so because of that, we can compute the stresses straight from the deformation solution. All right, so basically, I'm just in the interest of time, just because I want to make sure we do the next example before the break, right? I'm just going to give you the formula here. But basically, the way that we derive this formula is that we take the nodal forces in the local coordinates, right? So in the coordinates that are local to the element, hence the reason why it's a purely normal stress, and we just divide it by the area. Okay. So the stress in a truss bar, okay, which again is only computed after you compute the deformation. It's just like in ANSYS, right? So just in ANSYS, first thing we always compute is the deformation. Then from there, ANSYS computes everything else. Okay, so same thing here. So for a truss bar, we have E, the Young's modulus, divided by L, which is the length, multiplied by this vector. Okay, so the vector is going to be minus cosine, minus sine, cosine, sine. Okay. So you do need to know the orientation of the element itself. And then you're going to multiply that by a vector of the deformations of that element. So you have d1x, d1y, d2x, d2y. Okay. So I'm using node 1 and 2 here just as a placeholder, but just know that that vector there is the vector of deformations for that element. Okay? It doesn't necessarily have to be nodes 1 and 2. And so this sigma here is a stress that you can compute per element. So essentially, you would repeat this you would repeat this calculation for every element or every truss bar that you're interested in finding the stress for. Okay. Okay. So let me demonstrate how to do this just very quickly from the last example. Okay. So from the last example, we have two truss bars. We have both elements A and C. Okay, so let's start with element A. So the stress in element A is equal to E divided by L multiplied by this vector of sines and cosines, which if you remember for element A, the orientation angle for element A was 90 degrees. Okay. So cosine of 90 degrees is 0, sine of 90 degrees is 1. And so our vector, our orientation vector here is going to be 0, -1, 0, 1. And we're going to multiply that by the deformations associated with that element. Okay? So it's d1x, d1y, d2x, d2y. Okay? Because element A is connected to nodes 1 and 2. Okay, so if we plug in the value for these here, which we've already found from the problem, right? So d1x is 0.0033 inches. d1y is a minus 0.0167 inches. Okay. And then d2x, d2y, since node 2 is fixed, are just both zeros. Okay. Okay, and so if we compute this out, so we basically just do the vector-vector multiplication. And since we're doing a row vector multiplied by a column vector, we have essentially just a dot product between these two vectors. Okay. Then the stress in element A is 4,175 PSI, or pounds per square inch. All right. One nice thing about this stress calculation, just like in ANSYS, is we can interpret the sign of the stress as either being in tension or compression. Okay. So the fact that this stress is positive means that element A is in tension. All right, which makes sense, right? So if you look at element A in the previous problem, element A was that vertical element. And the force or the load that we're applying is a vertical force that's pulling away from element A, right? And so it makes sense that this element is in tension because it's supporting that vertical weight underneath it. Okay. Okay, now let's look at element C. Right? We can't compute the stress in a spring just because a spring just doesn't really have a concept of stress because it's a spring. Okay. So let's do the same calculation for element C. For element C, we have E divided by L multiplied by the orientation vector. And we know that for element C, its angle was 0 degrees, right? Because it's a horizontal element. Okay, and so the orientation vector in this case is going to be -1. So that comes from the minus cosine. Okay. Minus sine is 0. Cosine is 1. Sine is 0. Okay, and then we're going to dot product that with the deformation vector. So we have d1x, d1y. Okay. Now element C, right? Remember, we're multiplying this by a vector of the deformations specific to that element, right? So element C is connected to nodes 1 and 4. This is d4x, d4y. Okay. I'm not going to write their values again just because it's fairly straightforward. But d4x and d4y, those deformations are 0. Okay, so we plug this in, we do the calculations, we get sigma c is equal to minus 825 psi. Okay, so we have a negative stress here, and so negative stress means that our element is in compression. All right, so that calculation is pretty simple. It's pretty rudimentary, of course, but it can be helpful, right? And if anything, just for the purpose of computing whether your elements are in tension or compression. All right, any questions on this before we move on to the next example? Okay, all right, so I have one more example for 2D trusses, and this one actually introduces a new type of constraint, okay? So let's introduce that first. It's pretty straightforward before we do the example. Okay, so it's probably a constraint that you've seen before in your previous classes, hopefully in your statics class. And so that's the concept of a roller constraint. Okay. Okay. So with the previous example that we did in 2D trusses, we have been introduced to the fact that any given node can have multiple degrees of freedom. Okay. And what we implicitly kind of assumed in the previous problem was that every fixed support, right? If you have a fixed support on a 2D truss, that's going to zero out both of the degrees of freedom, right? So we can see that here. So nodes 2, 3, and 4, both of their degrees of freedom, the x deformation and the y deformation, are zeroed out, right? So there are constraints out there that only constrain or only restrict 1 out of 2 of the degrees of freedom, or maybe 1 out of more. So it's possible to have constraints that constrict only one. And in fact, we'll take this idea a bit further in the second half of class today when we talk about beams. Okay? So beams introduce another type of degree of freedom called a rotational degree of freedom, which we've kind of talked about already in activity 4. Okay. And so there are different constraints that can kind of constrain maybe only one or two of these degrees of freedom. Okay. So the first one we're going to introduce is a roller. So roller support looks like this. It looks like kind of a very simplified roller skate. All right, so for a roller support, we make the assumption that only the direction that's perpendicular to the surface is going to be constrained. So in the direction that's parallel to the roller surface, we actually just leave that, we kind of just leave that alone. Okay. Okay, so for this figure here, we can see that the dx deformation here is going to be free. Okay. Right, because that roller is in the x direction, so that means our structure is free to roll in that direction. Meanwhile, dy is going to be 0, just constrained. Okay. So I know technically, if you put a roller on a surface, it technically only constrains it. It technically only constrains the deformation in one direction, right? So that means, if you have a roller like this, technically it's only going to stop deformation in the negative y direction. Okay. But for just the sake of simplicity, for the problems that we're doing, we're going to assume that all y deformation is restricted, right? Even in directions that are kind of opposite from the surface. Okay. And so the way I usually illustrate it for people is, don't imagine this as just purely a roller. Imagine the roller is inside a trap, just like that. Right? Right. So the wheels are kind of free to go, in this case, free to roll in the x direction, but any movement or attempted movement in the y direction, the constraint is going to prevent. Okay, so that gives us a little bit of freedom, a little bit of flexibility in terms of how we do our problems. So sometimes a roller support is more appropriate for a given situation. Okay, any questions on this before we do our last example before the break? Okay, all right, so let's do one more example. I'm gonna go a little bit faster through this one just to make sure we finish before the break. Okay, but this example also is a little bit shorter just in general. Okay, so let's have a two truss structure with a roller support. Okay. All right, so it's going to be a structure that is attached to a wall. Okay. All right, so we're going to have one element here that is going to be slanted downwards. We'll call this element A. And another element here that's going to be purely horizontal. We'll call this element B. Element B is going to be connected to a roller. Okay, so let's go ahead and label the nodes. And so we're going to call node 1 here at the end. The other node that's connected to element A is going to be node 2. And then the roller support is going to be at node 3. Okay. All right, so we have some dimensions here as well. So we're going to assume that the length of element B here is 5 feet. And length of element A is 10 feet. Okay, and then in terms of load, we have a single load here. So we have a load that's kind of flying off or holding on the end here. So it is a load in the negative y direction on node 1, right? And then that load has a magnitude of 25,000 pounds. Okay, so let's also talk about the truss properties. And so both of them are going to be made of the same material. Okay, so both have a Young's modulus of 30 times 10 to the 6 psi. And we're going to assume that both have the same cross-sectional area, which is 1 inch squared. Okay. So for this system here, we're going to do basically our standard calculation. And so we are interested in computing the deformations of all nodes in the system. Okay. All right, so we have a pretty standard problem here. The only wrinkle here is that we have a roller support at node 3. Okay, so that's going to affect how we apply the boundary conditions near the end. But it starts in a very standard way. So let's go ahead and start with the element stiffness matrix. Okay. Oh, I'm sorry, I forgot one piece of information on the problem. we need to know the orientation of element A. So we can tell from the image that element B is horizontal, okay? But then to get the orientation for element A, we need that angle there. So we're going to assume that angle is 30 degrees. Okay. So this is our first time with what I would consider kind of a fairly awkward angle here. So anything that's not 0, 90 degrees, or 45 is a little bit awkward. So our sines and cosines, our matrix here is going to be a bit strange. And so just kind of be prepared for that. Okay. Okay, so let's start with the element stiffness matrices. Okay, so let's start with element A. Okay, so element A here. So we know it's going to be, we do have a weird angle here of 30 degrees. Okay. So first thing we need to determine is what its orientation angle is. Okay. Because that's going to affect how we compute the sines and cosines. Okay, so from the image, it's very tempting to set the orientation angle for A to be 30 degrees, because that's the angle that's given to us. But that's actually not the angle that you should plug in to sine and cosine. Okay? Let me explain why. Okay. If you look at how element A is oriented, and in fact, let me go ahead and draw it here by itself. Okay, so this here is element A. We have node 1 here on the left, node 2 here, or node 1 on the right, node 2 on the left. Okay. And this angle here is 30 degrees. So the acute angle that element A makes with the horizontal is 30 degrees. But what I'm saying here, or what I'm claiming, is that that's not the angle that you should plug in to your Truss element stiffness matrix equation, right? And why is that? Right? That's the only angle that's given here, right? Well, what I didn't mention last time, just because this just wasn't an issue with the past example, is that there is a certain convention that we need to follow when computing these orientation angles. Okay. In some sense, it doesn't matter what convention that you use. The only thing that matters is that it's consistent. So I'm going to give you my convention for this, just so that your answers are kind of consistent with mine. But if you prefer to do this slightly differently, that's fine. You're still going to get the same answers in the end, granted that you use the same convention for every single element. Okay. Okay, so here's the convention that I use. And so the convention I use is that I start from the node on the element that has the lower node number. Okay. So you're going to look at your element, right? Your element is going to be connected to two nodes, right? You're going to look at the one that has the lower node number index, okay? Which in this case is node 1. Okay? So this node, you can imagine that as your pivot. All right, so that's the pivot. That's where you're rotating around. Okay. Now, what you need to imagine is that the element with that as the pivot is oriented at 3 o'clock, and so it's going to be pointing in the positive x direction. And so essentially, we're going to imagine that our element starts like this. Okay. So using the lower number node as a pivot, right? Imagine that our hand or our element is kind of pushes out in the positive x direction. Okay. Right. So that's where we start. Now, that's not the orientation of the element itself, but In order to get the element into its orientation, we're going to rotate counterclockwise until we reach the orientation of the element that's given to us in the figure. Okay. So from that starting position of 3 o'clock, we're going to go essentially backwards in time. You can think of it like that until we reach the orientation that's given to us in. Okay. So essentially, we're going to start here and then rotate along that pink arc just like that. Okay. All right. So the amount that we rotate, so the amount that we kind of rotate counterclockwise, that's the orientation angle that we plug in. Okay. So you're going to have to use, sometimes you're going to have to use a little bit of trig here, a little bit of geometry in order to get this answer here. But you can see from this image here where if the given angle that we're given is 30 degrees, and that's with respect to a horizontal axis in the negative x direction, that means our orientation angle in order to get from 3 o'clock to our given orientation has to be 150 degrees. Okay. Okay, and so that is the angle that we plug into our element stiffness matrix. Okay. Okay, so that's the convention that I use, okay? Which again is not the only convention that's out there. But you know, if you want to keep things consistent, then you can just use this convention. Okay, we're going to apply this to every single element in order to compute its orientation angle. Okay, any questions on how we determine that orientation angle for that element A? Okay, good. Okay, and so from here we can just compute sine and cosine just like normal. Okay. So cosine of 150 degrees, and so now that's 150 degrees takes us into the negative x domain. Okay. So cosine is going to be a minus root 3 over 2. Okay. So even though 30 degrees is not as nice as 45 or 0 or 90, it is still one of the standard degrees. And so, you know, we do get a very nice expression for cosine. And then sine of 150 degrees is a positive 1/2. Okay, so let's go ahead and plug in and compute the element stiffness matrix for element A. Okay, so unfortunately there's no nice way to do this. You're going to be multiplying a lot of root 3's over 2's divided times 1/2. Okay. Oh, we also need to compute AE over L. Okay, so AE over L for this element here is 2.5 times 10 to the 5th. Okay. So that means our element stiffness matrix is 2.5 times 10 to the 5th divided by. I'm just going to write the values in here, but you know, definitely feel free to kind of check this on your own as well. 3/4 minus root 3 over 4 minus 3/4 3 over 4. Okay. And then we're going to multiply this by the degrees of freedom in element A, which is d1x, d1y, d2x, d2y. Okay. Because element A is connected to nodes 1 and 2. Right, and then just like we always do, let's go ahead and write them into the column. Okay. So everything in that first row, we're going to basically transpose it into the first column, just like we normally do. Okay, next we have the second row. So second row is we have a 1/4, root 3 over 4, minus 1/4. Rotate that down. Next row we have a 3/4 minus root 3 over 4. We write in the symmetric value, which is the minus root 3 over 4. And then finally, in the bottom right, we have a 1. Okay. So this is definitely something where you want to have MATLAB or a computer to do this, help you do this. Okay. Okay, now let's do the same thing for element B. First, let's get the orientation angle for element B. Now, for horizontal and vertical elements, it doesn't matter too much. You know, technically speaking, if you want to look at this element, right? So element B is like this. We have node 1 on the right, node 3 on the left. Okay. So if you want to be technical about it, you go by the same convention, right? Technically, the orientation angle for element B is 180 degrees, because right? So we take our lower number node, that's our pivot, and we just rotate counterclockwise until we reach the orientation. Technically, since the higher number node is on the left, we had to rotate 180 degrees. Okay? And so that does change our sines and cosines. So cosine of 180 is a -1, sine of 180 is 0. Okay? And so you would think that this affects our calculations, but basically anything that is cosine times sine is going to be 0 because sine is 0. And everywhere else that cosine appears without sine is just cosine squared. Okay. So the element stiffness matrix for a horizontal element, no matter if it's 0 degrees or 108 degrees, essentially looks the same. Okay. Okay. And so what we have is 1, 0, -1, 0, 0, 0, 0, 0, -1, 0, 0, 1, 0, 0, 0, 0, 0. Now we're going to multiply this by the degrees of freedom for element B, which is d1x, d1y, d3x, d3. And then the stiffness constant out in front, since element B here has a shorter length, that means the stiffness constant is also going to be larger because we're dividing by the length. It's 5 times 10 to the 5th. Okay. So element stiffness matrices in this problem, not too bad, right? The biggest wrinkle is mostly going to be how you compute that orientation angle. Okay. All right. Any questions on this? Okay. All right. So let's go ahead and move forward. So next we are going to work on the assembly. Now I'm not going to write the numbers into the assembly just because with all the root degrees here, it does get a little bit messy. But I will block out the areas just so you can kind of see what they look like. All right. So the good news with this element, with this problem here is that we only have 3 nodes. And so our global stiffness matrix here is only going to have 6 rows and 6 columns. Okay. So 2 degrees of freedom, X and Y, for each of the nodes 1, 2, and 3. Okay, so that should save us a little bit of writing here. So we have D1X, D1Y, D2X, D2Y, D3X, D3Y. Same thing for all the rows. So you have D1X, D1Y, D2X, D2Y, d3x, d3. Let's go ahead and write in the forcing vector as well. Okay. So let's go ahead and box out the element stiffness matrices. Okay. Okay, so first we have element A. Element A is connected to nodes 1 and 2. Right, so those are two nodes that are right next to each other in the system. So we're going to block out a continuous 4x4 block here, which looks just like that. And then element B is going to be nodes 1 and 3. Okay. So it's going to be these regions right here. This one right here. This one right here. Okay, and we're going to have zeros everywhere else.
No.
Okay. Good. All right, so next we're going to apply our boundary conditions. Okay. So for our boundary conditions here, we have two constraints. Okay. Right, so we have a fixed support on node 2. Okay, so node 2, that means we're going to knock out both the x and y deformations. Okay. So d2x is equal to 0, d2y is equal to 0. Okay. But on node 3, we have a rower support, right? And so we're only going to cancel out the deformation that's perpendicular to the rower surface, which is d3x. Right, so we're going to set d3x is equal to 0, but d3y we're going to leave free. So we're only going to affect the rows for d2x, d2y, and d3x, and the fourth and the row for d3y, we're just going to leave it alone. Okay, so let's go ahead and do just that. Okay, so for the d2x row, that is the third row in the matrix, and so we're gonna have zeros here, 1, 0, just like that. 0, 0, 0, 1, 0, 0. Okay. Okay, so rows 3 and 4 in the matrix look just like that. And just like we always do with our constraints, we're going to replace the entry in the forcing vector. Okay, so f2x and f2y are going to be 0 as well. We're going to do the exact same thing for d3x. So f3x here is going to be 0. Okay. And then just like the previous example, we just have one load. And so our load in this case is a 25,000 pounds, which is being applied in the y direction on node 1. Okay. So that means F1y is going to be a minus 25,000 and F1x is going to be 0. Okay, so all I did in that step was I added in those two loads there. Okay, so that's just a very basic application of the boundary conditions. Okay, normally you would think that you were done at this stage, but there is kind of one wrinkle to this problem that we haven't seen before just yet. We are at the break time though, so I don't want to mention that yet. So when we come back from break, we'll kind of mention what that wrinkle is and why it causes an issue. And that'll be the last point in trusses, and then from there we'll move on to beams. Okay. All right, well, let's take a break. Let's come back at 4:30, and then we will pick up with the last bit of the 16. Okay, it's 4:30. Let's go ahead and get back into it. Okay, so last thing we did in this example before the break was that we applied all of our boundary conditions. And so we applied our fixed supports, and so we had one support or one constraint on node 2. We're both constraining the x and y deformation. And then for node 3, we had a roller support where we only are constraining the x direction because that is the direction that's perpendicular to the roller surface. Okay. Now, I mentioned right before the break that there's one little caveat. There's one kind of a wrinkle for this problem, and so to actually see it, my laziness is kind of coming back to bite me. We do need to actually write in the entries of our assembly. Okay, so what we did before, just to save a bit of time, was that what I said was that I'm going to box out the areas where we're going to assemble. Right, so I made that big red box, and so that's where we are assembling the entries for element A. And for the blue boxes, that's where we're assembling the entries for element B, which is connected to nodes 1 and 3. Okay. So to actually see what's going on here with this wrinkle, we do need to actually insert the entries for element B, not element A. Element A is kind of gets a little bit crazy with the roots, but let's do element B at least. Okay. Okay, so luckily element B. Its element stiffness matrix is right here, right above us. Okay. So let's go ahead and put these entries in here. We're obviously going to skip the entries that have to do with the support. So we're not going to add this row. Okay, that row is already zeroed out from the roller support on node 3. Okay. But we are going to put everything else in. So let's start in the top left. Okay. Okay, so in the top left, we have the entry 1, 0, 0, 0. Okay. And then in the top right, we have -1, 0, 0, 0. Okay. And then from there, we have all the entries in the bottom row, which are all zeros. Okay, so that is the row associated with D3Y that is connected to element B. Okay. Okay, so that's basically all the entries that we have remaining here. So that's this one, this one, this one, and this one, all of them which are zeros. Okay, so why did I do that? Why did we kind of go through that exercise there? So I want you to notice something about this global stiffness matrix. Right? Let's look at the entire last row. Right? And let's look at the entire last column, right? So both the row and the column that's associated with D31. All right, what do you notice from that, right? Every entry in that last row and every entry in that last column are zeros. Okay, so we have an entire row of zeros, an entire column of zeros. Okay. Okay. Now, this doesn't necessarily have to do with the fact that we have a rower here. It's kind of just coincidence. Okay, so this can happen even if you don't have a roller support. Although for this particular problem, it happens in the case where you have a roller support. Okay. Okay. So the fact that it happened on a roller here was kind of just coincidence. Okay. But this shows kind of one actually very distinct thing. Okay. So if you try to solve this matrix, and so basically if you took this matrix as it is, right, and assuming that you input the entries for element A, okay, you try to invert the matrix you plug into MATLAB, what MATLAB will tell you is that this matrix system is actually impossible to solve. And so you'll get an error or you might get NaNs or not a numbers, okay? The reason for that is because if you have an entire row and an entire column of zeros and they correspond to the same degree of freedom, what that tells you is that this system is under constraint. So what does that mean, right? So when a system is under constraint, that essentially means that the configuration that we have shown, right? The configuration that we have shown in the figure here, okay, is not stable, right? And so this is not a shape. This is not a configuration that the system can hold. Okay. And it makes sense, right? If you look at the way the system is designed, right? So we're pulling downward, we're pulling downwards with a force of 25,000 pounds, right? Node two is fine, right? So node two is kind of fixed to that location there. But if you look at node three, right? If we pull down on this system, right? And node three has a roller support there, then what do we expect to happen in that situation? We expect that that roller is actually going to fall downwards as well, right? And so we don't have a static situation anymore. We have a dynamic situation. Okay, so this system is going to move. Right? So there's going to be some rigid body motion that's going to happen. Right? Okay. So what happens when you find an under constrained system? Well, one thing you can do is you can just kind of just throw up your hand and say this problem sucks, right? So this problem was not meant to be solved this way, which is true, right? So that's one way to kind of look at it. This is something that's important for you to kind of know for ANSYS problems as well, because this can happen in ANSYS as well, right? So even if you think that you fully constrain the system, right? You may have an under constrained system as well, and some of you have actually experienced this error too. Okay. And so some of you who have done, maybe some of this happens for some of you in ANSYS activity 2, for some of you in ANSYS activity 3, right? It may happen to some of you in ANSYS activity 4, right? So ANSYS has a very particular error called a solver pivot warning. Okay. So a solver pivot warning basically tells you that your system is under constraint, right? So there's not enough constraints in the system in order to prevent some kind of rigid body motion. Okay. And so the way to fix it, right? So the way to fix an under constraint system is the same in direct stiffness as it is the same in ANSYS, is that you need to add more constraints to the system to constrain this motion. Okay. Okay. Now, the easiest way to do that in direct stiffness is whichever column or whichever row where you're under constraint, you essentially turn that into a fixed constraint. You essentially turn that into a pin support. Okay. So you essentially treat that row as if it were fixed. Okay. And so, the way we do that, you're going to put a 1 on the main diagonal.
of that row. Okay, so just like we always do with the fixed support, and then you're going to put a 0 in the forcing vector. Right, so you essentially kind of modify the problem so that you can actually solve it and find a solution in the original configuration. Okay. Okay, so for this problem, right, our only issue here is with D3Y. So what we're going to do is we're going to eliminate this entry here. Okay. We're going to put a 1 here. So this 1 here is going to constrain D3Y. And then we also need to put a 0 in for F3Y as well. So essentially what we're doing in this problem is that we're transforming that roller support into a pin support or a fixed support, okay? So that's something that you would need to do in order to solve that kind of problem, okay? Now in ANSYS, right, when you get that solver pivot warning, that means you need to add more fixed supports, right? So sometimes all it is just providing a fixed support. Maybe you just forgot to put it in a particular problem. That's kind of uncommon because I would say that for the most part, applying a fixed support kind of just comes second nature. What's actually a more common cause for the solver pivot warning in ANSYS is that you have different parts in an assembly that aren't fully constrained with each other. Okay. And so if you get the solver pivot warning in ANSYS and you're sure that you have a fixed support in your model, I would check the connections in between different parts and just make sure that whichever parts are supposed to be bonded are bonded together. Okay. Now you can run into issues like if you remember from activity 4, where because we turned that geometry into shells and beams, we had to manually add the connections afterwards. And so it could be that when you're adding that many connections, maybe you miss one, right? And so you may get a solver pivot warning in that case. Okay. But just kind of wanted to make that connection of an issue that we see here in direct stiffness, and then kind of the exact same issue that you would find in ANSYS as well. Okay, any questions on the concept of being under constrained? Okay, all right, and so that's it for trusses. Okay, so we did kind of 2 examples with that. Right, so now we're moving on to beam elements. Okay, so of course, we've seen beam elements before, right? So I just mentioned ANSYS activity 4, right? So we saw beam elements there. And remember, the biggest difference between beam elements and kind of regular elements is the fact that beam elements can compute this idea of an element orientation or rotation. Okay. Okay, so the way that we kind of describe it is we say that beam elements can account for rotational degrees of freedom. All right, so what do I mean by that? So let me draw a beam element here. We have kind of our slender rectangle here. Okay. We're going to do kind of a simplified version of the beam. So we're only going to consider 2 degrees of freedom per node. Okay. All right, so on the left-hand node, this is going to be node 1. Okay. We're going to account for deformations that go transverse to the element itself. Okay. Right, so we're going to say that's D1Y, so that is what we call the transverse deformation. Okay. And then we're also going to account for or compute the rotational degree of freedom, theta 1. And then same thing on the other side as well. All right, so these are the beams that we're going to consider for this unit here, okay? So beams can support transverse deformation, so that's deformation that goes perpendicular to the length of the element. That's D1x and or D1y and D2y, and then what we call rotational deformations, theta 1, theta 2, which computes the orientation of the element at those locations. Okay, so any kind of change in slope or kind of rotations, we can account for that there. Okay, so for beams, unlike trusses, so remember for trusses and springs can only support what we call axial deformation. So that's tension and compression. So beams have the other degrees of freedom, which are rotation and transverse deformation. Okay, so we're gonna have basically two different element types that kind of handle two different types of deformation for our systems. Okay. Technically, there is an element that can support all three modes of deformation. So axial deformation, transverse deformation, and rotational. Okay, so we call those frame elements actually. So those ones are kind of crazy. And because, if you think about it, for a frame element, each element there has 6 degrees of freedom, right? So 3 modes of deformation per node, and there's 2 nodes, so that's 6 overall. And so the element stiffness matrix for a frame is actually 6 by 6, which is, maybe doesn't sound crazy, but when you think about it, 6 by 6, a 6 by 6 matrix means that there are 36 entries in the matrix that you have to compute. And if you're doing that for every element and there's 5 or 6 elements in your system, that's a lot to compute over a short period of time. Okay, so we're gonna work with a simplified beam, right? So for a simplified beam, very much similar to a 2D truss, we have 2 degrees of freedom per node, so 4 degrees of freedom per element. Okay, and so for a beam, okay, in this simplified form, we'll have 4 degrees of freedom per element. So that means our element stiffness matrix will be 4 by 4. And a 4 by 4 element stiffness matrix will only have 16 entries for us to compute, just like the 2D truss. Okay. And also, just like the 2D truss element, there is symmetry here as well. So you can definitely leverage that symmetry when computing these matrices. Okay. So 16 entries, much better than 36. All right. And so with beam elements here, there is theory that governs beams. Okay, so there is the whole idea of a beam equation that's derived from the kind of the concepts of Euler and Bernoulli. Okay, so Euler-Bernoulli beam theorem is probably something you've learned in your solid mechanics class. We're not going to go through the derivation just because I think there's enough for us to go over with the direct stiffness problems. So I'm just going to give you the element stiffness matrix, and then I'm going to explain all the different variables that go into it. Okay. All right, so this one's going to look a little bit strange because we're going to have rows and columns that correspond to the angular deformation, rotational deformation. Okay. Okay, so for the element stiffness matrix, we have the following. So first we have our factor out in front. So we have EI divided by L cubed. Okay. We'll find all of those in a second. And then we have a 4 by 4 matrix. where we have our four nodal degrees of freedom. Okay. So just like we had in the figure up here, our 4 degrees of freedom are d1y, theta 1, d2y, theta 2. Okay. So we have a transverse deformation and a rotational deformation as well. Okay, and so the entries in the matrix are the following. So first row is going to be 12, 6L, minus 12, and then 6L. Okay. And just like our 2D truss, our matrix here is symmetric. So that means we can take the entries in the first row, transpose it down into the first column. Okay. So this one's going to go here. This one's going to go here. This one's going to go here. Okay. So 6L minus 12, 6L. I'm really emphasizing that trick with the symmetric matrix because it really does save you a lot of time. Okay. What you're going to find, especially when you start doing the homework, you're going to be spending a lot of time computing these individual entries in these matrices. Okay. So anything you can do to kind of save yourself some time, leverage the symmetry in these matrices will help you in the long run. Okay. It may not seem that much per problem, but when you're doing this over and over and over again, all those little time savings will add up. Okay, second row. So second row, we start in the diagonal entry, which is 4L squared, and then minus 6L, 2L squared. Okay. Once again, we're going to write this entry into the column, and so we have a minus 6L and a 2L squared. Okay. Next row in the matrix, we have a 12 and then a minus 6L. That minus 6L is going to be transposed down into the last row. And then finally, our last entry is 4L squared. Okay, so that right there is the element stiffness matrix for a beam element. Everything in yellow there is symmetric with something that is above the main diagonal. Okay, all right, so let's go ahead and define all of the variables here because there's a lot of symbols here. Okay. First we have E. So E here has the same definition as our truss bars, and so E here is the Young's modulus for the beam. So that depends on the material. That's almost always given to you. Okay. Next, let's go with L, because L also is a familiar friend. So L here is the length of the beam element along the axis of the beam. Okay. And then finally we have I, right? So we have that capital I that's out in front. Now, if you remember from activity 4, right? When we talk about beam elements under that context, right? So when we extract beams in ANSYS, right? What did we say was one thing that ANSYS saved for each or stored for each beam? What we said was that ANSYS stores information on the cross-sectional shape, the cross-sectional area. Okay. Now, the reason it does that, or one of the reasons it does that, is because beam elements need to know what the moment of inertia of its cross-section is. And that's exactly what I is here. Okay. So of course, the moment of inertia depends on the size of the cross-section, it depends on the shape, right? So an I-beam is going to have a different moment of inertia than an H-beam. Actually, I and H are the same. I beam is going to have the different moment of inertia as an L beam or a cylinder rod, right? Okay. There's other things that ANSYS uses the cross section for. It's not just solving for the moment of inertia, but for our calculations where we're just doing transverse deformation and just rotations, then the moment of inertia is enough. Okay. Now you're not going to have to know how to compute this. I know it's been a while. Even I kind of struggle to remember how to compute moments of inertia. So for the problems that I'm going to give you guys, the moment of inertia, you can think of it as just another property, another parameter that's going to be given to you in the problem. Okay. But I thought I would mention it in terms of what it is, just so you kind of understand what you're plugging into these. Okay. Okay, and of course, D1y, D2y, that is the transverse deformations, and then theta 1, theta 2, those are the rotational deformations. Those are already defined as well. Okay. All right, so that's the element stiffness matrix for the beam element. So again, we're skipping the derivation here, but just know that this element stiffness matrix was derived based on beam theory. All right, any questions on the element stiffness matrix for the beam? Okay, cool. All right, so next thing I want to introduce is let's bring back the concept of the constraints. Okay, so now that we have a rotational degree of freedom, theta 1, theta 2, we need to kind of revise our constraints because we need to know which constraints are going to be actually restrictive of the angular deformation versus just the translational deformations. Okay. So just a little bit of terminology, right? So axial deformations, which is tension and compression, and the transverse deformations that we just kind of talked about here, I would consider those to be the translational degrees of freedom, okay? Whereas theta 1, theta 2, those are the rotational degrees of freedom, okay? So different constraints are going to affect these degrees of freedom differently. And so in fact, for the problems that we're going to be doing in this class, there are 3 different types of constraints that you need to kind of know how they affect our system. Okay. So the first one, and I admit I've kind of been abusing this term here, is what's known as a fixed support or a fixed constraint. So a fixed constraint, and this is true within ANSYS as well. A fixed constraint is the most powerful constraint that you can apply. It's going to place limitations on all degrees of freedom. Okay. So that includes the axial deformation, transverse deformation, and the rotational deformation. Okay. Now, the way that fixed constraints are typically shown is it kind of shows like it kind of looks like the beam is kind of stuck into the wall or kind of welded into the wall. Okay. So it usually looks something like this. And so you have your beam, okay, this. And so fixed support looks like it's just kind of glued to a wall, just like this. All right, so let's say you have a wall there. And so whenever you have a wall, we can assume that the wall has 0 deformation. And so if you have a beam that's just attached to it, that is what your fixed support will look. Okay, and so just like the description says there, all degrees of freedom are kind of knocked out at a fixed support. Okay, so that means dx is equal to dy is equal to theta is equal to 0. Okay, okay, all degrees of freedom. All right. Next, we have the concept of a pin support or pin constraint. So a pin constraint will only restrict the translational degrees of freedom, so dx and dy, but it will leave the rotational degree of freedom free in order to do what it has to do. Okay. Okay, so a pin support looks like the following. Okay, so a pin support looks like there's a pin there and it's attached to something that's fixed to the grip. Right, so it looks something like this. So it's attached to a pin and the pin itself is attached to the grip. So for a support like this, okay, dx is equal to dy is equal to 0. Right, so the translational degrees of freedom are constrained, but the angular degree of freedom is not. So theta here is 3. Okay. So if you saw a pin support in a system, right, then you do not zero out the rho that associated with theta. Okay, and then the last degree of freedom that we have is the roller support, which we had just kind of finished talking about. But it is worth mentioning here that the roller support also does not constrain the rotational degrees of freedom. But I'm just looking ahead a little bit, just kind of see which one we did. We should be able to finish by halfway through tomorrow. Okay. Okay, so for a roller constraint, it looks like the following. We have a beam just like this. It's attached to a pin, and this pin is on wheels. Okay, so for this configuration, we can see here that dx is free. Just because the x direction is the direction that's parallel to the roller surface. Okay. dy is going to be constrained. Okay, so because the y direction is perpendicular to the roller surface, and then the theta, the rotational degree of freedom, also is free. Okay. Okay. So for beam problems, you have to be a little bit a little bit more careful with the constraints because there is a difference. That the main thing that's going to trip you up is going to be the difference between a fixed constraint where all degrees of freedom are set to 0 versus the pin constraint where the theta is still free. Okay, and so you need to make sure that when you apply your boundary conditions, you account for that kind of nuance thing. All right, any questions on the types of constraints that we can have in our beam problems? Okay. All right, so let's do an example. So this example here is pretty straightforward. In fact, there's no numbers. But I do like to go over just because it's a good illustration on how to deal with the different constraints. Okay, so let's look at a very simple two-beam system. Okay, so we have one beam. This first beam here is going to be fixed to a wall. And that's going to be attached to another beam, just like that. Okay, so first beam here is going to be beam A. Second beam is going to be element B. Okay. We have our nodes in the system, and so we have node 1 that's attached to the wall, node 2, which is right in between elements A and B, and node 3, which is at the end, just like that. Okay, node 3 here is actually going to be constrained as well, but it's going to be constrained with a pin. Okay. Another thing that we will apply here, the fact that we have multiple degrees of freedom here at each node, that means we can apply loadings in each of those degrees of freedom as well. Okay, so we're not limited to just one load per node. Okay, we can have multiple loads per node. Okay, and so for instance, on node 2, okay, we can have a transverse force, so we can have a force P that's going in the negative y direction, and we can apply a torque as well. Okay? And so let's say at node 2, we're also applying a torque of magnitude n. Sometimes torques are called moments. I try to kind of keep it consistent, so that's why we give it the symbol capital M. M stands for moment. Okay, so we can apply a torque or moment directly on the node, which we can do now because we actually have a rotational degree of freedom that's going to support that. Okay, and so for this particular problem, both elements are identical. We're going to have the exact same values of the Young's modulus, exact same length, exact same Young's modulus, or exact same moment of inertia. Okay. And so what we want to do simply here is just let's write out the global stiffness matrix along with all of the loads and constraints. Okay, so again, no numbers here. This is just kind of a very simple kind of symbolic problem. All right, and so with that, and since both elements here are identical, there's kind of really no point in writing out the element stiffness matrices. Okay, but we'll go ahead and do it just once, just so you can see, right? So the element stiffness matrix is just going to look just like this, right? So without any numbers to plug in, we can just have the symbols. Okay, so the element stiffness matrices for both problems, for both elements. We have E times I divided by L cubed multiplied by 12, 6L minus 12, 6L. 6L minus 12, 6L. 4L squared minus 6L, 2L squared. Utilize the symmetry to write that down into the column. And then we finish up writing up the element stiffness matrix just like that. Okay. Now, of course, the two elements are connected to different nodes, and so we do have to account for that. But in terms of the values of the element stiffness matrix, especially when we don't have values to kind of plug in, they're just going to have this kind of flux just like that. Okay, so let's go ahead and move on to kind of what this problem was kind of more about, which is the assembly. All right, so for assembly, we have our global stiffness matrix. And so in this case, we have 3 nodes, right? So nodes 1, 2, and 3. And each of them are going to have 2 degrees of freedom. So they're going to have transverse deformation as well as a rotational deformation. So that means our global stiffness matrix here is going to be 6 by 6. Okay, so let's go ahead and write that in here. Okay. So we have D1Y column, theta 1, D2Y, theta 2, D3Y, theta Y, theta 1, 2Y, theta 2, D3Y, theta. Okay. And since for some reason I wrote this offset into the center, let's make our forcing vector on the left. So on the left here, we have F1Y, M1, F2Y, M2, F3Y, M3. So I'm using the symbol M's there to kind of denote the moments applied on each of the nodes. Okay, so M1, M2, M3. Those correspond to the theta 1, theta 2, theta 3 rows. Okay. So not too big of a global system here. So 6 by 6 definitely is much more on the reasonable side. So let's go ahead and insert our element stiffness matrices. All right, so let's start with element A. So element A we know is connected to nodes 1 and 2. Okay. So every row, every column that's associated with nodes 1 and 2, we're going to box that out. Okay. I'm not going to write the values in just because, again, this is kind of more of a theoretical problem. But, unlike the previous problem that we just finished, right? We know that every entry in our element stiffness matrix is non-zero, right? So there's no circumstance, unless our element had a length of 0. But if we had a length of 0, then we wouldn't have an element anyway, right? So there's no non-zero entry here. So what you're going to see is that we're not going to run into the same issue before. We don't have our system is going to be fully constrained here. So there's no fear of having an under constraint system. Okay, and then element B. Element B in this case is going to be connected to nodes 2 and 3, which again is fairly straightforward. Those 2 nodes are right next to each other in the matrix, but it's going to shift where we insert them. Okay, and so those are going to be this region. So you can see that we have all rows and all columns kind of covered here. And so there's no risk of having a row of entire zeros or a column of entire zeros. Okay. Okay. All right. But for this problem, the assembly and the element stiffness matrices, not that interesting because, again, we're not kind of fully computing them. Okay, so let's get to applying the boundary conditions. And so let's kind of illustrate to see kind of how the different boundary conditions affect our matrix here. Okay. Okay, so first we have a fixed support on node 1, right? So node 1 is fully fixed, and so that means all degrees of freedom at node 1 are going to be set to 0. So that means d1y and theta 1, both are going to be 0. Because we have the constraint that's fully fixed at that location. Okay, so that means that the first two rows in this matrix, so the row associated with d1y, the row associated with theta 1, both of those are going to be zeros, except for a 1 on the main diagonal. 1, 0, 0, 0, 0, 0, and 0, 1, 0, 0, 0. Okay. And of course, we're going to have zeros in the forcing vector as well. That fully set those degrees of freedom to 0. Okay, next constraint that we have is a pin support on node 3. So you can see node 3 here is not fully fixed, and so but we do have a pin. Okay. And so the relevant quantities for this problem, that means d3y is going to be 0, okay? Because remember, a pin support will constrain and knock out all the translational degrees of freedom, but theta 3 is still free. Okay, so we're not going to change the theta 3 row, but we are going to change the row associated with d3y. Okay. Okay, so we come to our system here, right? So the d3y row is the second to last one. Okay, so let's go ahead and insert zeros here with a 1 on the diagonal. And then f3y is equal to 0. Okay, so those are the constraints for this problem. So, the main thing is that for a pin support, remember, we don't constrain the rotational degree of freedom, only the translational. Okay? Okay, so those are the constraints. Now let's go over the loads, right? So for the loads, we have 2 of them here, right? So remember, it's possible to have multiple loads at the same location, okay? And so we have a load of minus P applied in the minus Y direction on node 2, okay? So that means F2Y here, we're just going to set that equal to minus P. Okay. The other load that we have on node 2 is a torque of magnitude M on node 2, okay? Now for torques and moments, you do have to be a little bit careful with the sign, okay? So the sign does matter. And so in this particular problem, this torque M, is going in the counterclockwise direction. Okay. All right, so if you kind of trace the path around for that torque M, it's going in the opposite direction of a clock, hence it's counterclockwise. Okay. And so the sign convention that's typically used for a right-handed person, the right-hand rule, a counterclockwise torque is we consider that to be positive. Why that is, it's just a convention, right? And so it's one of those things where it doesn't really matter what the convention is. It only matters that everyone follows it, right? And so I think this more has to do with the fact that there's more right-handed people in the world than left-handed. Okay. But since our torque here is counterclockwise, that means we're going to input a positive M in our matrix here. Okay. If the torque was going clockwise, and so if it was going in the opposite direction, then we would put in a negative M. Okay. And remember, that sign does matter, right? So remember, that's why we put in a negative P in for this, in for F2Y, because that load is going in a negative Y. But for M2, okay, since our mode is going in the counter, or since our torque is going in the counterclockwise direction, we're going to input a positive N. Okay, and then last thing we're going to do is we note that there's no load or constraint that's being applied on theta 3, right? So there's nothing that's affecting it. And remember what we do in those cases, we apply the stress-free boundary condition, which is just a 0, and everything in the matrix on that row, we leave that alone. Okay, all right, and so that's the that's the procedure here. So not too much. You just have to kind of be aware of the different types of constraints that are there. Okay. Any questions on this example here? Okay, good. All right, so I have one more example for today. I'm hoping we can finish it, but if not, we can finish it up first thing next time as well. Not the most complex example. So the nice thing about beams, we are working with kind of relatively simplified geometries here. I'm not going to give you a beam that's angled at a different angle. So every beam that I'm going to give you is either perfectly horizontal or perfectly vertical. Okay, so you don't have to worry about any kind of angularity. Okay, so that does simplify things a bit. Okay, so before the next example, let me kind of remind you of something that we talked about last week, which is the concept of reaction forces. All right. So I want to bring it up again just because we've kind of expanded our repertoire of different constraints. And so that means that reaction forces is kind of something that's worth repeating. Okay. All right, so reaction forces, what are they? So remember, reaction forces, these are forces that are being applied onto our structure at the locations of the constraints. Because remember, according to Newton's second law, right? According to Newton's second law, that if we want to have a structure that is in equilibrium, or in other words, is static, that means the sum of all the forces on the structure or the object has to equal 0. Okay, we kind of neglect that a little bit, or we kind of get away from that definition with finite elements just because we have this idea of constraints. But one thing that is kind of implicit that we kind of establishes that these constraints are actually applying forces to our model. We just don't compute them in the normal sense. Okay. I'm going to expand this definition a little bit. Okay. So reaction forces only occur at constraints or only occur on certain degrees of freedom that are being actively constrained. And so if you have a constraint that is only constraining certain degrees of freedom, but leaving other ones free, we're not going to have a reaction force in the degrees of freedom that are free. Okay. Okay. And so with the introduction of the rotational degrees of freedom, that means we can also have reaction torques as well. Okay. But we can only have reaction torques when we have a fully fixed support. Okay. So that means pin supports cannot exert a reaction moment. Same thing with rollers, right? So rollers, you can only have a reaction force in the direction that is perpendicular to the roller surface, okay? So for directions or degrees of freedom that are not being constrained, you should expect there to be no reaction force on those, okay? If you get one, then it probably means that you computed something incorrectly in your calculations. Okay, so last week we talked about how to compute reaction forces, but let's kind of have a quick reminder. All right, so remember, reaction forces is something that you can compute after you compute the deformation solution. Okay, so you compute the deformation solution is something that you do after. Okay. So after you compute the deformation solution, and so you're going to basically have that as a vector, you're going to multiply that vector by the global stiffness system that you had before you apply the boundary conditions. So it's basically the linear system that you had after you did assembly, right? So after you've assembled all the contributions from the element stiffness matrices, but prior to applying the boundary conditions, okay? So you would have, so basically that system there would be a fully symmetric linear system, which again, remember, we can't solve normally, but you can multiply that by a deformation solution, and then the resulting vector is going to be your reaction forces. Okay, so we're going to do that in the next example, which maybe we'll finish, maybe we won't. We'll see. Okay. The next example is also unique. So this will help you with your homework as well. And that this example is actually going to combine beam elements and springs. Okay, so we're actually going to see how that's actually done as well. Okay, but any questions on this before we kind of jump into our last example for the day? Okay, all right, so let's go ahead and do our last example for today. Okay, so for this example here, we're going to have a beam, okay, a two-element beam that's supported by a spring. All right, so we're gonna have a beam. It's gonna be fully fixed to a wall. Okay, so we have a fully fixed support here on the left-hand side. One beam like that, another beam like that. And the right end of the beam is going to be supported by a spring, which we're going to treat as a spring element. Right? Okay, so the first beam that's attached to the wall, we'll call that element A. Second beam that's right next to it, we'll call it element B. The spring we will define as element C. Okay. Let's write in the nodes. So the node that's fixed to the wall, we'll call that node 1. The node that's in between elements A and B, we'll call that node 2. The node that's at the very end of the beam, we'll call that node 3. And then the node of the spring that's attached to the ground, we'll call that node 4. Okay. Okay, so let's talk about the beam properties. So we're going to assume that both beams are identical. So they have a Young's modulus of 210 gigapascal. They have a length of 3 meters. And they have a moment of inertia of 2 times 10 to the minus 4 meters to the 4. Okay. So moment of inertia has a weird unit. It's actually length of the fourth. And so we actually need that to balance out all the units in the system. Okay. All right, and so the properties of our one spring. So the spring only has one property, which is its spring constant. And so that's 200 for this problem, 200 kilonewtons. All right. And so we also need to have a load, otherwise the system's going to do nothing, right? And so our load is going to be applied at node 3. And so it's going to be purely a transverse load, so no rotational component at all. Okay? So this load here, we'll give it the symbol P, has a magnitude of 50 kilo. All right, and so I believe that's everything that you need for the problem. And so from here, we're going to compute. So for this problem, let's compute all the nodal deformations and rotations. Okay. In other words, we're just going to just solve the problem like we usually do, right? So we're going to apply our direct stiffness method. And the other thing we're going to compute is all of the reaction forces as well. All right, and so after we compute all the deformations in the problem, we're just going to multiply that by our global stiffness matrix that we did before boundary conditions, and then that will give us our reaction forces. Okay. Okay. All right. Any questions on the setup for the problem? Okay. All right. So let's go ahead and get started. Right. So first thing is we need to compute all the deformations in the problem. So we are just going to go through our direct stiffness methodology. Right. So something that you're probably sick of at this point, but like I said, all these problems kind of proceed the same way. The only difference is just the details in the element stiffness matrix. Okay, so let's do that first. So we'll start with the element stiffness matrices. Okay, so our two beams in this case, just like our previous example, they are identical. Okay, and so they're going to have the same element stiffness matrix, but their nodes are going to be different as well. Okay, so for this problem, I actually the way I have it here, just to kind of make things a bit easier to kind of write down, I have everything in terms of symbols first, and then we'll go in and plug into the numbers later. Okay. Okay, so first we have element A. So element A is a beam element. Okay, so that was given to us in the problem. And we know its Young's modulus, we know its length, and we know its moment of inertia. Okay. So its element stiffness matrix is EI divided by L cubed divided by 12, 6L minus 12, 6L, 6L minus 12, 6L, 4L squared minus 6L, 2L squared. Last two rows, we have a 12 minus 6L. And then bottom right, we have a 4L. Okay, element A is connected to nodes 1 and 2, right? So that's going to give us the our degrees of freedom. So that's going to be D1Y, theta 1, D2Y, theta 2. Okay, and so I know for this problem we have the numbers, but we're going to leave it off just for now. The reason I'm leaving it off, you'll see in a second once we do the assembly. So it's a little bit easier to kind of see the assembly for both the beam and the spring if we kind of do it together, or we do it in terms of symbols first. Okay. Okay. So for element B is going to be exactly the same. So the values for element B are the same. The only difference for element B is that it's connected to nodes 2 and 3 as opposed to 1 and 2. Okay, so element B also is a beam. It's going to be EI L cubed. We're going to go write the exact same thing. By the way, I'm using a different coloring here just to denote the entries that are symmetric. You don't have to use different colors. I'm just doing it just to highlight just the symmetry. But feel free to just use the same color for all of them. That's perfectly fine. Right, and then of course we adjust the vector of deformations to account for the nodes that element B is connected to. Okay, so it's D2Y theta 2, D3Y theta 3. Okay, good. So elements A and B pretty straightforward. It's a lot of annoying kind of plugging in, but again, make use of the symmetry to kind of help you out with plugging in. Okay. All right, and then finally we have element C. Okay. Now, there's a couple of different ways you can treat element C. Okay, so there is I would say the traditional way, which is more cumbersome, or you can be a little bit clever here and kind of do it in another way. Okay. So one way to look at element C is that we have a spring that's vertical, right? And so if we treat this like we did earlier today, right? So this is essentially a spring that's in two-dimensional space, okay? Remember, the way that we did this was that, we have basically a 2D spring. We have our arm of the clock here that's at 3 o'clock. Okay. And then what we can say is that in order to rotate the spring into its current configuration, we have to rotate counterclockwise, this case, by 270 degrees. And so what you can say is that for element C, so element C here is a spring. We can say that its orientation angle for element C is 270 degrees, right? So that means cosine of 270 is 0, sine of 270 is -1, okay? And then we make our element stiffness matrix like the following. So we have K, we have a 4 by 4, okay? And so we fill this in with the combinations of cosines and sines that we had before, and treat this kind of like just a pure 2D problem. Okay. So that's one way we can do it. And this is not wrong, by the way. And so you can definitely do it this way, but it's a little bit cumbersome. Okay. Because if we kind of just make an observation here, right? Let's come back to the figure. Let me go ahead and erase all this pink stuff here. All right, so let's make an observation. And so we know if we look at node 3 right here, right? So let's focus on that one. Okay. Node 3 is attached to two elements, right? So node 3 is attached to this beam B, and is attached to a spring C. Okay. Now that's significant because, right, we know the types of deformations that these types of elements can support, right? Beams, we know, can only support transverse deformation and rotation. It cannot, right? So at least in the simplified beams that we're considering, beams cannot support axial deformation at all. Okay. Whereas springs, spring can only support axial deformation, which in this case, for a spring that's vertical, right? An axial deformation is a deformation only in the y direction. Now, the reason I'm bringing that up is that if you look at the deformation modes that are supported by these two elements, neither element can support any deformation in the x direction, right? And so if you look at that beam, right, the beam cannot support axial deformation. So the axial direction for that beam is the x direction. So there's no way that beam can support x deformation. Okay. Springs, on the other hand, right, this spring is vertical. Spring is vertical. And so that means that it also cannot support any deformation in the x direction at all, okay? Because the spring is vertical, it can only go up and down in this case, okay? And so if neither element connected at node 3 can support deformation in the x direction, there's no need for us to include it in our global stiffness matrix because it's just going to be a row of all zeros, okay? So let me write that down here. So since there's no way for deformation in x direction to be supported by the elements at node 3 or just in this situation, okay, there is no need for us to include it in any of our calculations. So that's both our element stiffness matrix and in our global stiffness matrix. Right. So even though for technically for a 2D spring, right, we would technically have to include that x direction just because that's how a 2D spring is, right? If you actually plug in, right, so if you actually plug in these sines and cosine values, right, This is one, for a vertical element, vertical elements are actually very easy to do, okay? In fact, the results actually support that conclusion as well. Okay, so you actually computed the element stiffness matrix. So you went through and multiplied all the sines and cosines and zeros and ones, you get this. Okay. And if you look, right, the entire first row, the entire first column, the entire third row, the entire third column are all zeros. Okay. So what does that tell us, right? So that tells us that there's nothing constraining, or there's no stiffness in that direction, right? And so if we were to include D3x and D4x in our analysis and in our assembly, we'd end up having to manually constrain it anyway, because we get something that's under constraint, okay? So to save yourself a little bit of time, right? So if you kind of notice these things, and you notice and you know for sure that there's no way that D3x, D4x are going to be non-zero in any way, okay? You don't have to include it in the element stiffness matrix, okay? And so the easier way to do element C is to kind of make note of that. Okay? Right, so we can make note of that and basically treat it as if it were a 1D problem, only in that Y direction, okay? And so our element stiffness matrix for C can be just simply this 2x2 matrix, the good old 2x2 spring element stiffness matrix of K minus K minus K, K, okay? Multiplied by the deformation vector, D3Y, D4. Because again, there's no point for D3x and D4x to be there because they're just going to end up being zeros at the end anyway. Okay, just as we illustrated here, and just as we kind of reason, just kind of based on the configuration and the types of elements that are there as well. Okay. Okay, so you can save yourself a bit of writing, and so that'll save us 2 rows in our assembly, which we'll do tomorrow as well, by just kind of making notice of something like that. Okay. All right, any questions on this before we wrap it up for today? Okay, all right, so that's all the time we have for today, and so we will finish up this example tomorrow, and then we have one more concept with under direct stiffness before we switch gears back to ANSYS, which is the idea of distributed loading. Okay, all right, so we'll finish that in the first half tomorrow, and then we'll move on from there. So thank you guys for coming today. Hope you guys have a good rest of your evening, and I will see you guys all tomorrow.
Right.
You too. See you all.